Swayam Prabha. Digital India. Educated India.
Okay, shall we get started? Good morning. Thanks for being here on a Saturday morning. This lecture I will go through with you simulation of nonlinear response function, at least the tools that we have in order to easily estimate nonlinear response function for a generic Hamiltonian. So if I'm given an Hamiltonian, how am I going to write down all possible level pathways, Feynman diagrams, and then estimate? I mean, one might say, okay, this is a bit of complicated implementation, but there are three important tools which are already available, open access, which enables us to do this. Firstly, to treat and develop your system Hamiltonian, diagonalizing it, and defining your density matrix, so on and so forth, you have QTIP, right? So you kind of have seen how to work with QTIP, and that's where we kind of define our system and also solve the equation of motion, right? So because QTIP solves this. Now the thing is how that solution of density matrix is then used to calculate your impulse response functions. That's where a bit of complication is, and that involves two things, right? One, you should be able to write down all what we are calling diagrammatic perturbation theory. You should be able to write down all possible UL pathways, making sure you remove all the cancelling of pathways and keeping the ones which follow time ordering and so on and so forth. It's not impossible to do for a 2-level system, 3-level system. It's reasonably simple to do, but as you go in a more generic and more complicated kind of situation, it can become a bit complicated and tricky to kind of evaluate. So we are going to use for that purpose a Python package, which also can be pip installed. So this is called UFSS package, and this is from Peter Rose and Jacob Critch. So they have, I would say, pretty nice JCP paper. I can send you this paper as well, part of the notes. So this one is a Python package. It can generate Feynman diagrams for any nonlinear optical spectroscopy up to 5th order. Okay, so it's actually pretty bad for linear. I mean, the Feynman diagram is very simple for linear response, so you don't really represent it. But second, 3rd order and 5th order, this particular package generates pretty nicely your Feynman pathway. So somebody has written this, the program automatically identifies for a given system Hamiltonian what are the possible excitation pathways. Okay, so we are going to use that. Now that is only looking at generating Feynman diagrams, and how are we going to use it to actually estimate the nonlinear response function? For that, we have our second package, and that second package is called QDPy. This was developed by my theory collaborators, mostly Eric Bittner, Andrei Piryatansky, Carlos is an experimental guy, but whom I collaborate with as well. And most of the work was developed by Shah. Shah is currently a scientist at Los Alamos National Labs. How is at Montreal with Carlos Silva. Eric Bittner is in Houston, and Andre is also at Los Alamos. So what this tool is going to do is that it kind of uses QTIP as the basis to define the system, and also use UFSS package to identify all legal pathways, all the diagrams, and then goes on to kind of calculate your nonlinear response function. It's kind of very nice and easy to use. Okay, so I'll send you these papers, these two papers. By the way, there is GitHub for PewDiePie as well. You want to explore, you can also get source code. There are some few bugs with the source code, mostly with the plotting aspect that we are sorting this out. It's not complete yet, so it's going to be, there's a lot of work still needs to be done on PewDiePie, but we are going to slowly kind of upgrade it as we go along. Okay, so this is going to be our primary tool. Okay, so keeping that, let's start coding simple stuff. So I want everybody to open Colab if possible, and we'll go through this together. Hopefully you have internet connection. Everybody has Colab open. Colab.research.google.com. Open a new file. So always Colab has all your NumPy and everything, Matplotlib as well, but Colab does not have Qtip, PewDiePie, and UFSS. So these are the three packages that we need to install. So the first step is installing those packages. So pip install Qtip, pip install UFSS and PewDiePie. So pip install is good because you can install the most latest release. Instead of you downloading the source code and doing it yourself is probably a better way to do it. Okay, once, let me give a few more seconds for that. Yep. Yeah. Yeah. I'll tell you. PewDiePie is a separate package. You need to pip install that also. Or you can download the source code and put it in the same directory as your code, and then you could possibly use it. It has a bunch of fun. So even UFSS and PewDiePie are two independent packages like Qtip. So for the sake of today, I would suggest just using Colab. It's simpler. But if you are interested in looking at the source code, I would go to GitHub and probably you could even install it from GitHub. Okay, anyway, for the sake of, we can kind of go over it together again. Let me go over at least calculation of response functions, and then we can go over the code again. So from UFSS, UFSS can do a lot more than Venn diagrams generation, but we just need the diagram generator. So we just need to import from UFSS dot diagram automation. From diagram of automation, you import diagram generator. So this is for making the interaction diagrams, and you also will need, of course, NumPy. So okay, so these are the two important, you need the diagram generator, and the first step, we will set up the interaction diagram. So basically what kind of, so nothing about the system, it's about what kind of diagram. Is it refacing, non-refacing, true quantum, or linear response, on and so forth. We just need to set that up. Yep. You're not able to install, pip install. What is the kind of error you're getting? Oh, really? I'm actually surprised about this. We'll put this UFSS. Huh? Is okay? Okay, so diagrams are tuples in this package. So you just need to define a variable. So let's call this DG. This is your diagram generator, right? So that's your suppose, and you're going to say, let's say we start with linear response. So you call this R1 the first response. That will be DG. Okay, now we have to set what kind of visual pathway or the correlation function that we are interested in. Let's say we are just interested in the linear response, so we just need to define that in the property of R1 or the first. Let's say set phase discrimination. So that sets okay what kind of interaction it is and also the phase of the interaction. So whether it's a bra or a ket and so on and so forth. To do that, you define a variable. So I'm going to say 1, 0. So there is only one interaction, field interaction from the left. That's why I put 1 here. So this is how I'm going to define my. Okay, so that's done. I also want to define my field interactions, and usually you define pulses and b dot array. Let's say from -1, 1. This becomes even more clearer once you have nonlinear response. Don't worry about it now. See, let's say now we need to get E field times, which will simply be pulse. This becomes even more clearer once we write, because one field interaction, it doesn't make any sense to define times. It's like we'll define it later. This is basically setting the pulse interval, but there is no pulse interval here, so it's kind of arbitrarily defined. So let's not worry about it right now. So how do you create a diagram now? So I'm going to say my first R1 will be R1 ST dot get diagram and we'll say 0. Okay, I'm going to call this refacing, but it doesn't. For now, it's not refacing; it's linear. But I'm going to use the same thing. Okay, so this is basically the syntax for generating your diagram. As I said, I kind of quickly went through it, go through the help me file on GitHub on UFSS. That's pretty nice. I mean, guy has written 2 papers on this. We kind of go over that. So this enables you to kind of define your label pathways. Of course, here we have a boring label pathway. It's not a linear response, but it can set that up pretty well. Just a note is that this is not really made to generate a linear label pathway. So it's going to give out something. The diagram is going to look weird. Bear with me because it's not meant to do that. But you'll see, it will generate reasonably good stuff. Just copy my previous code. Such that it's not a better way of doing. Okay, that worked. Okay, so that's your diagram. Refacing diagram is pretty simple. It's just so the way it's going to generate is it's acting from the ket and going up, means exciting. So that's a linear response. That's a diagram. So if you think of the diagram, you can go either from the ket or the bra side. You can go either excite or go up or U or emit or down, right? So there's other things. So the way it generates is now it is acting from the ket. Because that's how I said to act. The phase discrimination is set such that my field is going to act from the left, and it's going to excite. So AU. So it kind of generated the appropriate diagram. That's kind of a brief introduction to how UFSS works, so how you kind of write diagrams. Okay. Later on, we will write the refacing and non-refacing as well. So now, so that's just the excitation pathway, but that's not enough. You need to define your system. And defining your system, it's all done using QTIP and QDPy. From QDPy, you need a couple of things. So let's import them. So you import all the classes of QDPy and also some plot functions. There is a plot function that we will use. It's called Silva plotting, named in the honor of Carlos Silva. But so we'll use part of that if I had to import that. Okay, now we have to construct the Hamiltonian. So that's an important thing. Construction. By the way, do you want me to wait till you kind of execute this, or? Okay, let's wait. Execute this till this part. By the way, if you have problems both with UFSS and QDPy, there are very nice examples online. Shah, who was a primary driving force for QDPy, has written very nice examples. And you can also contact him if needed. He said he would respond. So, what makes it linear in the code is here. So if there are more, so this is single interaction. If there are more interaction, you have to extend this variable. So I'll show you. So here I'm saying one field interaction. So it's 1, 0 acting from the left side. If, for example, I had another field interaction, then it becomes some 0, 1. And third field interaction could be 1, 0, for example. Okay, now this becomes, this phase discrimination is the one where I set saying how many interactions I have. Yeah, so basically, if you think about this, these are the wave vectors and the frequencies of the fields that are interacting. Okay. In fact, in this phase discrimination function, this happens to be the pulse width in femtoseconds. So here I'm putting 1 femtosecond, but I can put 10 femtoseconds. So this just shows that if I'm 1, 0, I'm setting it up to act from the left. If I, on the other hand, have something like this, then I'm setting it up to act from the right. And number of those terms will tell you number of field interactions. Then it takes care of the time ordering and stuff like that. So the UFSS package takes care of time ordering to ensure that, to eliminate any kind of unnecessary. It's just an array for interaction. So it later on will define another array, which is actually, this is just to ensure time ordering. It needs some kind of temporal variable to kind of place these sort of variables in time. It becomes clear once we make nonlinear response. If it's not clear, I mean, it's implemented in a particular way. It's a kind of a tool to manage time ordering in UFSS to generate correct, appropriate time. Okay, is everybody fine with this? That is fine. Let's go ahead. Now we have to define the Hamiltonian. Okay, you can come back to this again if needed. You have my code, so you can kind of go through my code. It's actually written with collaboration with Shah. So I have to acknowledge Shah in helping in developing this Jupyter notebooks. Very important. So for constructing Hamiltonian, we just start with a two-level system, ground and exact state. So some variables there is to just define energies, right? So I just write everything in electron volts. So I'm taking my transition energy to be about 1 electron volt, and of course we need to write in terms of frequencies. Now the most important thing is, of course, the interaction strength or the dipole strength, light matter interaction. Let's call that variable mu1. Let's say that is also 1. Then we have to actually define your operators. So I'm going to talk about the lowering operator of the system. The H naught kind of is defined for that. So I call this an A. Q-tip, destroy, let's say 2-level system. So if you remember, Q-tip has this function destroy, and that will enable you to, lowering operator. Lowering operator. And your dipole moment operator is dipole strength multiplied by E dot tag plus A. And your Hamiltonian now, basic Hamiltonian, will be H. I mean, I'm going to use directly the thing, but H bar times W1, the energy, A dot tag, A dot tag times A. That's your basic Hamiltonian. So now you need to define system path coupling. And for system path coupling, you will use collapse operators. For the sake of this class, let's assume you don't have any inhomogeneous static disorder, just homogeneous line width alone. Remember the Lindblad operator for that. We have to define that. I'm going to define some parameter. Use another name. So I call kappa instead of gamma. Okay, that's not a big deal. I call this some 0.1. We need to define our Boltzmann constant. Electron volt. I'm also calculating at finite temperature. So let me all put that together. Because there is some finite occupation of your ground state at room temperature, of the excited state at room temperature because of some thermal population of the states. So that average number of thermal population will be 1 over e power e1 eta minus 1. So this thing. So given all that, now I can define my relaxation operator and excitation operators C1 and C2. You need to have both of them. C1 will be NB dot QRT, right? Kappa star 1 plus 1 star A. So this is your relaxation. So if you remember, just note that usually you just write square root of gamma times A. I added this N1 because there is a finite occupation of the excited state. So in principle, I could have a stimulated emission process, which will be proportional to the density of the state in the excited state. So I added that. And once you have stimulated emission, you should also have excitation condition. So that will be your C2. These are your two collapse operators. P dot SQRT. All right. That will simply be kappa times N1 multiplied by A dot tag. This is your excitation. So from here, you can add how many ever more you want. If you have inhomogeneous broadening, you can have another collapse operator, different kinds of bars. You can keep on ordering collapse operators. But then at the end of it, for the sake of QT-pi, actually it's coming from QTIP, you need to kind of bunch them all together into a list. So we are going to define COPS to be a list of C1, C2. Okay, so basically here I define my unperturbed Hamiltonian H0. Here I am defining system path coupling with simple decay with some decay rate kappa, and we know the collapse or the Lindblad operator associated with it is square root of kappa times A. We also considered some possible thermal population, thermal Boltzmann occupation of the excited state. In that case, we have to also add stimulated emission in the relaxation pathway in our collapse operator. Of course, then I have to also consider that in the excitation operator, which will be inhibited because there's already some population, thermal population sitting there. And then I have to bunch all the collapse operator into a list. Let me go over this quickly, and then you can go back and I'll paste the cleaner version of this so that you can go through the thing. So we have defined the Hamiltonian, we have defined the system path interaction, but that's not enough, right? at the end, what we need to solve? We need to solve for the density matrix. So we need to define density matrix. So that I'm going to define rho. There is a function in QTIP called FOC-DM, which generates this density matrix. There are different ways of doing it. We have seen one way in the examples of QTIP that I have given, but this is basically ground state Hamiltonian. It's a 2 by 2 matrix. Basically, what FOC-DM tells you is the dimensionality of your matrix, and then here you say where is my starting point, what is my initial condition. So here I'm saying, of course, the FOC-DM really works well if I have population either in the ground state or excited state, somewhere in between. Kind of, I don't know how to do that, but it says 2 by 2 matrix, and my population is my zero ground state. So that's basically my ground state of the Hamiltonian. And my system now is the thing. So this system is basically defining the entire thing. So there is a function called system, which will take my Hamiltonian, my density matrix, my lowering operator, dipole moment operator, system path interaction, which is through list of Lindblad operators or the collapse operators. And let's say we want this diagonal. So that's how we define the system. For the sake of clarity, I have a better, more well-commented version, so I'm going to copy that, paste it here, so that you can copy it nicely and also understand what you are doing. Where N1 comes from? Yeah, so when you do the excitation operator, the collapsing thing for the excitation operator or the Lindblad part of it is basically if I have an occupation on top, then it will not allow my excitation. So your Lindblad operator associated with blocking of the excitation is because of the population. So that's why when in the excitation operator, I will have my population of whatever the thermal population of the excited state, and not the other ways. Does it make sense? Yeah. So one note there here, I'm writing this in terms of Lindblad operators and not explicitly the Bath operators. So I'm not defining the Bath operator. So I'm kind of capturing all of that using a Lindblad, and then I can write my Lindblad equation, which is what this will solve. That's because I don't know exactly how to define my Bath operator, so I'm kind of not defining. By the way, all of this is basically within QTIP, so it's how you also work with QTIP. So it's beyond nonlinear response function. If you want to effectively capture system path interaction, quantum dynamics per se, this is how you kind of do about it. And the critical point is to be able to define your Lindblad operator. Okay, now let's say you define the Hamiltonian. Shall we go ahead or should I wait? Okay, so we define the Hamiltonian system path interactions, very nice. Now let's use QDPi to generate impulse response functions, not the actual optical response, just the system response functions. So for that, there is a function called diagram donkey. It's a funny name. So it takes, basically you need to give some kind of temporal, let's say, window over which you are looking at after the interaction has happened. So it's kind of looking at the impulse response evolution as a function of time. Here I'm going from 0 to 100, so seconds, and you're giving which kind of diagram, Feynman diagram that you need to give here. And we have chosen linear response. We have used UFSS to define that. So if I run this, Hopefully it will work. Okay. So that's your sort of expectation values of the so-called dipole and the number. So dipole basically is a coherence term, and that is oscillating, right? For some reason there is a phase flip. I don't know why, but we'll talk about it later. So that with one field interaction, you're generating that coherence, and that coherence is oscillating at the frequency of the energy difference. And a number, of course, is zero because there is no population. So that's what this kind of reproduces. Okay, fine. Yeah, come again. Oh, sure. Why the number is zero? Which number? The 0 to 100 there? There is some problem. It's not, I don't know how to, it didn't show me earlier, now it's showing up, so maybe I made some mistake there. So, I don't understand what you're asking. This one? Dipole is not zero, right? It's oscillating. Or number because it's population. With single field, there is no population. You're not creating a population with one field interaction. You're generating only coherence. Now, I don't know why this suddenly the EOPS failed. Okay, but it gave the right diagram, so it's fine. Okay, so that's a response function. It's just to see whether your response is working well or not. And what we need to now calculate is the actual response. In this case, it's a linear response, and QD-Pi has an inbuilt function to calculate linear response alone. How it does is basically solves the equation of motion numerically, and then like the impulse response function is known, does all the Fourier transform and stuff like that to finally show you a spectra. Let's run that. Can I go ahead? Do that. The function is, again, you're always using the system that you have created, linear underscore spec. Here I'm letting it scan. So here, remember, when you're calculating your spectrum, what matters is you're taking a Fourier transform, which means I need to set some kind of total temporal window over which I'm collecting the oscillation, right? And the resolution time step. Now, if you know Fourier transform, the total time window that I choose is going to determine the spectral resolution, right? Spectral resolution of the spectrum that I'm going to observe. Okay, so let's see. I chose 200, okay, because you can kind of see that it's actually not completely decayed. So maybe I want to let it decay further. Sometimes, again, there is a Fourier transform thing. If I'm Fourier transforming an oscillation, and if the oscillation has not completely decayed, at the very end, you'll have an abrupt jump. It's like, rectangular function, a square function, that will add noise. It will add additional frequencies, which you don't want. So it's better to either wait till everything has relaxed, or you kind of add a window function. Okay, otherwise Fourier transform will give you artifacts, additional frequencies which are not real. Okay, that's because of a numerical how you do discrete or even fast Fourier transform. Okay, so that's the thing. So here I'm waiting. I'm going to wait longer so that these things will completely decay. Let's do that. Okay, so there is a little bug in the source code in the sense that it prints the entire thing, which you don't want. I just need the plots. This is something which we should fix soon. Okay, this is your real and imaginary part of the response function. So in principle, if you can measure, so with one field, you generate linear polarization. This is emitting radiation. If you can do a time domain measurement, which you cannot easily do, but let's say if you can do a time domain measurement, then you will see that response oscillate in this particular way. So then you take this response, Fourier transform it, you get this. beautiful absorption and dispersion line shape. There is a bit of, again, a code error issue here. There is, especially with linear response, there is some kind of flip between the labels. Here it's just a plotting issue. So what is plotted as real is actually imaginary and otherwise. They kind of make sense. And you have done Kramer's chronic, right? An absorption feature. If I have an absorption, you'll have your imaginary part to be nice Lorentzian and your real part will be dispersive, and that's what it is. So there is a flip of the just plotting. You're not you have to go up. You don't get it? No? How am I getting? I'm the same QT pie as you. You also? You're getting? Okay. No clue. How is it? Huh? You got it? It was hidden somewhere. All right. Everybody okay with this? Kind of what we went. So we first define your pathway, and for defining pathway, we need to use UFSS. That's our primary package. We define your Hamiltonian, and have any system path interaction, but then your signal will never decay, and you don't want to be doing that. So you need to add some kind of, and I use a simple linear relaxation term. That's Lindblad operator square root of some relaxation. In this case, I call it kappa, we can call it gamma, whatever, the rate multiplied by your lowering operator. The only thing that I did was I explicitly put down some thermal population excited state. So that will add to your Lindblad or the collapse operators. Okay. Once I have that, then I go there. You can do diagram donkey, but you don't need a diagram donkey. What you need is directly this. The only two variables that, the important variable that you need to do is, you have to have diagram donkey, otherwise it will not calculate. So the way you have to have diagram donkey, then it calculates your impulse response functions, it keeps in the memory, and then when you call this function, it then generates your actual response. Okay, solves. Okay, let's take a small break now, and then we can come back and see how we can do nonlinear response.